Our starting point is to consider that the seismic cycle is a stick-slip sequence as proposed by Brace and Bayart in 1966, and that actually earthquakes are just like the onset of sliding of a frictional system. Then we actually make a link between a seismic fault. I can't switch my slide by just pressing the arrow. Okay, it works. We make a link between a seismic fault and this very simple frictional system, which are two blocks pressed together. I'm sorry, I just have, how I think I stopped sharing my screen. Does it work right now? Ah, here it is.
No, it seems
No, you are sharing, Elsa. We can see everything.
Okay, is it? Okay,
Yeah,
great.
looks good for us, Elsa.
Okay. Then we are interested in this very simple frictional system where two blocks, solid blocks, are pressed together, sheared, and then when shear becomes large enough, it slides. And we are interested in the rupture mechanisms at the interface between the two solids. Then, in your community, of course, you know that the onset of sliding is an earthquake, and then it's a rupture that propagates along the fault or along the frictional interface that breaks the solid contact, and that then allows sliding to occur. But actually, if we look at then from my experiment, my very model system, the onset of sliding would be due to the propagation of an interfacial rupture, as I schematize it here, and invading the whole interface. But if we look at and then, yeah, I have listed here some basic geophysical challenges that can get answers from the lab, from model experiments. We can think of understanding the dynamics of the rupture events, like the difference between slow and fast events, and that's something that we will discuss today. We can have some things to say about the prediction, both in time, when an earthquake will occur, but also in size. What would be the magnitude of the event if it would start, if it would be triggered now? We can consider the question of the zones that should be monitored. I have in mind the role of slow earthquakes on the activation of locked portion of a fault. And of course, we can test step by step the role of fault complexity on model faults, like by adding liquids, ground rock, roughness, etc. Then I can't switch my slides. I have to click 3 times. Okay. Then I say that in your community, of course, in our community, we know all that the onset of sliding is due to a propagative rupture, but actually it's not that obvious for physicists, in particular if we consider the Coulomb friction law. What is the Coulomb friction law? It says that the onset of sliding occurs when the shear force is equal to the normal force, and that press the blocks together, times a static friction coefficient, mu s. And as the blocks start sliding, the shear force needed to keep them sliding is the normal force times the dynamic friction coefficient, mu d. And in the Coulomb friction law, it is considered that the static and dynamic friction coefficient are independent of the contact area of the two blocks, and that there are material parameters. Actually, it took a long time before to have some microscopic interpretation of this Coulomb friction law with Bowden and Tabor in 1950. And they understood that actually when we press two blocks together, only the higher asperities will make contact. And the real area of contact is much smaller than the apparent one. And therefore, when I apply a normal force on this system, I have a huge pressure deforming the micro contact. Let me put this, yeah, deforming the micro contact at the interface. And we often consider that the contact reach the yield stress, the plastic limit of the material. Therefore, the real area of contact is equal to the normal force divided by the yield stress of the material. Now, their hypothesis was to say that at the onset of sliding, I need to bring the contact to the shear strength tau r in order for them to break. Then the shear force at the onset of sliding should be equal to the shear strength of the contact times the real area of contact. And then I get to this equality where the shear force is equal to the shear strength divided by the yield stress times the normal force. And here we can identify this ratio with the static friction coefficient, which is indeed a material parameter. However, the huge hypothesis here is that at the onset of sliding, all the contacts break simultaneously. They all reach the shear strength tau r at the same time. And this is not the case. As you know, at the onset of sliding, we have a rupture propagating along the interface. And actually, this Coulomb friction law is too simplistic from a macroscopic point of view. Because the law F equal mu S times N, macroscopic point of view, I want to stress that, assumes that all the contact breaks simultaneously and then there is no spatial degree of freedom. Then we cannot account for the spatiotemporal dynamics of the rupture. I insist on this macroscopic law because, of course, if we use the Coulomb friction law as a local friction law, I don't say that it doesn't work. But if we use it as a macroscopic one, we will only consider the motion of the center of mass of the system. And then using that, we cannot account for the propagation of a rupture at the onset of sliding. What actually happens is that some contact will break at a point, and then the neighboring contact will break one after the other, and this rupture will invade the whole interface. And what we will see today, I will show you the experimental proof that this interfacial rupture is a pure crack in a sense of fracture mechanics. It's a shear crack, a mode 2 crack. And of course, this is not a new idea. It's been thought for a long time. But the clear experimental evidence is quite new. It's been provided by Svetlitsky and Feilberg in 2014. Then if I come back to this schematic view of a fault, I actually got the inspiration from François Renard's talk, who presented some kind of picture like that. Then when a frictional rupture propagates, or when an earthquake propagates, the seismic rupture propagates along the fault, there's a rupture tip with a concentration of the energy that allows propagation. And then there is slip behind the rupture tip with all kind of complexity. I've shown here some off-fault damages, but of course you have pressurization, flash heating, chemical changes along the fault. But today, with my model system, I only consider the propagation of the rupture tip. For now, I won't say anything about the slip processes that occurs behind the rupture tip. And I think that that's very an important point, maybe for the later discussion, that we really care about the dynamics of this very singular point.
Elsa, can I ask you a question? Because this is some things that I never completely understood. How can you separate the two? Because if I look to the dynamic loading at the crack tip, the point the points behind the tip that are sliding are transferring load to the tip. So the real energy and the real load at the tip is also depending on the sides of the breakdown zone and the sliding zone behind the tip. How can you separate the two?
Well, when a crack propagates, it propagates because there is a flux of energy coming from the large scale to the rupture tip, and then this rupture tip accelerates to the sound speed. What happened behind is actually accounted for in the amplitude of the singularity, in the stress intensity factor. Actually, we will see it later. I have the equation in my talk. But what happened well behind doesn't interact with the crack tip, because the information cannot travel from the tail of the crack to the crack tip. In an infinite size system, infinite size system, then I have a reflection of waves. And then, of course, my crack tip will interact with its history. But in a model system where we consider an infinite size system, then we only consider time before any reflection of waves, then actually this rupture tip cannot have information from the tail, to my understanding. Then for me, I don't see how the tail can actually load the rupture tip during a dynamic event. I'm talking about the propagation, not the initiation or the nucleation phase. Does it answer the question?
No, not completely, honestly, because actually the Nabarro problems, when you compute the stress field behind the tip, you have a kernel that is exactly measuring how much load the multiplication between the kernel and the slip velocity behind the tip is telling you which is the load transferred to the tip. But this is the elastodynamic equation. So unless we do a complete separation of scale, therefore this means that this zone where this transfer is really inside the tip, which would imply that this sub C is microscopic. But in any case, this is my problem that I do not completely understand. Yeah, no,
you're right that to apply fracture mechanics, we have to assume a separation of scale between the cohesive zone and the elastic part of the solid. This is the small scale yielding hypothesis.
Yeah, exactly.
Yeah, because then we consider for elastic fracture mechanic, we consider the rupture tip as a point. And because it is not a point, we just regularize the elastic field at a point. And then, yeah, here I don't say anything about what happens in the cohesive zone. Yeah. We know there are processes that weaken the contact. We say that's the zone where the stresses are actually diminished. Yeah, I understand. Thank you. Yeah. Well, we can maybe discuss it in the second part if you.
Yeah, exactly. It'll be a perfect thing to come back to. Yeah.
Okay. Then here I have summarized some experiment where of the characterization of the rupture tip. Of course, it's not exhaustive, but I wanted to mention a characterization using strain gauges, then measurement of the elastic field surrounding the propagating rupture, then with analog materials, and this is the study I will show you here with PMMA, but it has been done also on rocks in the group of Greg McCluskey. There is this approach by the group of Lapusta and Rosakis, doing particle velocimetry, but same thing, following the elastic field as the rupture propagates. It's just another technique. Experiment where they use both the strain gauges, but they also use acoustic to localize ruptures. And this experiment by Latour et al. In Grenoble, where they actually use technique of elastography to measure very small deformation in the bulk of the material and tracking the rupture as it propagates. Of course, it's not exhaustive. And here it's only studies about the dynamics of the rupture tip. I don't mention all the studies about rate and state friction and evolution of friction with sleep and all this stuff. And that's very narrow field. And in this talk, I will present you, of course, the experiment we will discuss, and then I will show you that why we say that the frictional rupture is exactly a pure shear crack. And then we'll get interested into the dynamics of the rupture, both during the propagation with the equation of motion of the crack as it propagates and the arrest conditions. And I'll try to open the discussion to how it might be relevant for earthquakes. Then the experiment, you probably know it. It's been developed for a long time. It's an experiment where we press 2 blocks of PMMA, which is a transparent plastic. Then the dimensions are typically 15 centimeters times 10 centimeters and 5 millimeter thick. We press them together and we have 2 types of measurement: the real contact area measurement and the elastic field measurement. Then we actually visualize the real area of contact using total internal reflection. What we do is that we send a light sheet on the bottom block with an incident angle larger than the angle of total internal reflection. What it means is that at the interface at the frictional interface where there are no contacts, I have an interface PMMA air, and then the light is reflected. But where I have contacts, I just have PMMA, and the light is transmitted. And actually, when I record the transmitted light, I actually get a record of the real area of contact at a specific location. Then we actually record it with a fast camera at almost 600,000 frames per second, all along the interface. And we average in the transverse direction of the thickness in order that we consider our interface as unidimensional. Our second, and I'll show you of course, the measurements in few slides. Our second type of measurement is the 2D strain tensor along the interface, very close to the frictional interface, the closest possible actually, which was 3 millimeters. What we do is that we stick strain gauges that are little rosettes. You have a schematic view of it here. There are 3 resistances that are glued on the block. And then when the block is deformed, it actually varies the length of the resistance. And therefore, we get some variation of the tension coming out of the gauge. Then with this rosette configuration, we actually have access to the 3 components of the 2D strain tensor, all along the interface that we record at a high rate of 1 megahertz. We use, I won't discuss it too much, but I will use it as a tool. We consider dry interfaces, which means that there are just 2 blocks of PMMA clean, pressed together, and the surfaces are rough at the micron scale. And we will use also lubricated interfaces. And actually what we do is to coat the interface with a thin film of oil. When I say coat, is that we are not in full lubrication, it's not full of oil. We only have a very thin film that covers the interface. And you'll see that it will actually make a big difference. Here's a typical experiment. We start by pressing the 2 blocks together. Then we apply a normal force. Yeah, here it's in kilogram, about 400 kilograms. and that corresponds to about 5 megapascal normal pressure. And then we shear the system. We have different way to shear it, but let's start with the homogeneous shearing by translating this stiff carrier here. And doing that, we actually reach this stick slip regime where we have a succession of sliding events. Now, if we concentrate on 2 sliding events here that you see here, I show you some measurement of the contact area along the interface. Then those are just for illustration. They are not the one that we actually use for the study, but it's to show you the long time scale dynamic of the interface. Then what we see here is a spatiotemporal plot of the contact area. The x-axis is along the interface, 200 millimeter, the length of the block here. And the y-axis is time, here in seconds. It's the same time as the experimental time here. Each line is a snapshot of the real area of contact at a given time. And we normalize this plot by the first line. Orange color is 1, meaning that we have an intact interface, constant contact area, and colder color are a reduced contact area. Then what we see here is that when this first slip event occurs, we have a reduction of the contact area, and the line that you see here is actually the frictional rupture that traverses the interface. And then on a long time, the system stops and then heals. And that's what you see here. This is just the aging of the contact. Then because we don't have a homogeneous normal stress along the interface, the healing is not the same on the left side and on the right side. But there is time for aging. And then a new slip event occurs and then traverses an intact interface that has been reformed in the meantime, during the arrest time. Now we will look at a single rupture, but with a higher frequency of imaging. Then this is what we see here. Then same plot, spatiotemporal plot. X is along the interface. Y-axis is time in milliseconds this time. We use the 600,000 frames per second rate of the camera. And each line is a snapshot of the real area of contact. And what you see here is the rupture propagating along the interface. It starts here on the left side, it propagates and it accelerates until about 30% of the Rayleigh wave speed. The Rayleigh wave speed is the speed of sound on a free surface. Then here the Rayleigh wave speed is about 1200 meters per second for our material. Then this rupture here is responsible for the onset of sliding of our frictional system. Now we will look at the elastic field surrounding the rupture as it propagates. And I told you we will see that this rupture is a pure crack. Is a pure shear crack. Then let me introduce the few elements of fracture mechanics that we need. Then we consider here brittle elastic fracture mechanics. Then I can consider a solid under tensile loading here or under shear loading there. Here it is. And then elastic fracture mechanics tells us that there is a strain or stress singularity at the rupture tip going like 1 over square root of R. And further away from the crack tip, we have contribution of non-singular term. Then as we already said during the introduction, elastic fracture mechanics considers the rupture tip as a point. And then all the zone around the rupture tip is a singular zone. But then because it's singular in R, when R goes to 0, strain or stress becomes infinite. And this doesn't occur, then of course there is a regularization of the stress in what we call the process zone or cohesive zone. Not exactly the same definition, but we kind of switch between the two terms. And then the propagation criterion for a crack is that the crack propagates when the energy flux coming from the loading from the large scale balances the fracture energy, which is the energy dissipated at the crack tip per the creation of the new surfaces. Then if I summarize, in our frictional system, when the rupture propagates along the frictional interface, then I have shown this rupture as the red line here. At the rupture tip, there is first a process zone in green, then surrounded by a singular zone, and then surrounded by a finite non-singular zone dominated by the geometry of the system. Now what we want to do is to compare our strain measurement to the solution of fracture mechanics, then to this singular term. On the left here, I show you the strain measurement for a rupture, for a slow rupture. And you have here the three components of the strain tensor, the shear, the epsilon xx, the compression along the interface, and the epsilon yy, the normal strain. And then we want to compare our measurement to this solution, which is the singular solution with K, the stress intensity factor, the amplitude of the singularity. And F is a known angular function. But remember that our strain gauges are located 3 millimeters above the interface. Then actually we want to use the solution for y equal 3 millimeters, then varying r and theta in order to keep this y location. And this solution here is the one that has been plotted here on our data. Then the agreement is excellent. And there is here only one fitting parameter, K, the stress intensity factor. And the stress intensity factor is related to the energy flux from the large scale to the rupture tip that we call G, the energy release rate. And remember that our propagation condition is that the energy flux balances the fracture energy that I have called gamma here. Then by writing this propagation condition, actually, I can link the stress intensity factor to the fracture energy of the interface. Then by fitting this data here, I get a measurement of the fracture energy of the interface. Fracture energy in the sense of fracture mechanics. Then for this interface, gamma is about 1 joule per square meter. Then what we learn with this slide is that these detachment fronts are pure shear crack in the sense that the elastic field driving the crack are exactly described by the theory of linear elastic fracture mechanics. And the second thing is that by performing strain field measurements, we actually have access to the fracture energy of the interface. And now I want to convince you that this fracture energy is something physical. We measure it of the order of 1 joule per square meter. What is it? The fracture energy of the PMMA, if I take a plate of PMMA and I break it, is about 1 kilojoule per square meter, 1,000 times higher. But we have to remember that we have a frictional interface with very few contacts. The real area of contact is much smaller than the apparent one. We have actually a sparse interface. And under our pressure condition, we can estimate that the real area of contact is about 0.5% of the apparent one. It has been measured by Dietrich and Kilgore in 1960. Second thing is that when the frictional rupture propagates, it only weakens the interface. It doesn't break all the contact area. Of course, the two blocks are not floating one at the top of the other after the rupture passed. Then we actually reduce the contact area by only about 20%. Then now, if I consider that I have to break a material that has a fracture energy of 1 kilojoule per square meter, but I break only 0.5% of it, and only 20% of this 0.5%, I get to 1 joule per square meter. Then actually our measurement of the fracture energy makes sense with the physical properties of our material, considering that we have a sparse interface that is only weakened, but not fully broken. The second evidence that this fracture energy is something physical is its variation with the normal stress. You see from this small calculation that gamma is proportional to the real area of contact, right? But we've said before, looking at the Bowden and Tabor interpretation of the friction law, that the contact reach their plastic limit. Therefore, the real area of contact is proportional to the normal stress. Because more normal stress, more spread of the contact, and then I increase the contact area. Then actually, do I have a proportionality between the fracture energy and the normal stress? Then we did this measurement of gamma for several experiments where we varied the normal stress applied on the system. And we indeed found that gamma, the fracture energy, is linear with the applied normal stress. And this gamma is simply a measurement of the contact area that has to be broken to allow sliding to occur. Okay, this was for a dry interface. Now I told you that we will use lubrication as a tool. And let's do the same experiment, but we coat our surfaces with this thin layer of oil. Then first of all, what we observe is that the macroscopic behavior is quite different. On the left side, you have the loading, the shear force normalized by the normal force versus time for an experiment. And we see this stick-slip sequence that we have already seen. And for a lubricated experiment, we also have a stick-slip sequence, but of course, the static friction coefficient is reduced. That's what we expect from lubrication. And the drop of force is much larger when we add the lubricant. Okay. But in both cases, if we track the rupture at the onset of sliding, we find them on the contact area measurement, and there is no difference in the mechanism. We have a rupture propagating along the interface and then allowing sliding to occur. This is for the dry case, this is for the lubricated. Then of course, lubricated, we have more light passing through the interface because we have capillary bridges. That's why the colors are so different. Now let's look at the elastic measurement along the interface as the rupture propagates.
Elsa,
Yes.
can I ask you please a question
Sure.
about the previous one? The colors are also different because the range of areas
Yeah.
are very different, right?
That was my point, but not clearly expressed.
But why is there such a huge change in?
Then here on the dry case, we have a reduction of the contact area of about between 10 and 20%, depending on the experiment, the experimental conditions. In the lubricated case, here we see a reduction of about 50%. But part of it is due to the fact that we break more contacts, and we will see just after that. But part of it is only due to the fact that we have capillary bridges around the contacts that doesn't give strength to the contact, but actually when they appear as larger than in the dry case, then actually the light will pass through the oil in the capillary bridge, and then you have more light passing, and when you break the contact, you lose more light. But it doesn't mean that actually the real solid contact was much larger. And that's the main difference. Then it's some kind of one part is physical, the other is some kind of an experimental artifact. We actually haven't been able, we did, but it's quite hard to use this contact area measurement as quantitative, because it's not that the light passes only through the solid contact. We have also a part that passes through evanescence, meaning that when the two surfaces get close enough, but without contact, then the light will pass through the interface. Then we can't map exactly 1 pixel to 1 unit of contact area. And that's why we always show the variation of contact area, and we never really go into the numbers. Okay, then now we look at the strain field as the rupture propagates. Then here is the data you have already seen, or maybe a different set of experiment, but same thing for the dry case. And here are the data for the lubricated case. And the black line is the fracture mechanics solution, the singular solution. Then the fit is correct as well. But the main difference here is that actually for the dry case, under the same normal stress, for the dry case, the fracture energy is about, sorry, I don't see my slide because I have this band here, is 2 joules per square meter. But for the lubricated case, it's 10 times larger. 20 joules per square meter, 23. Actually, we were puzzled by this result at the beginning because we say, okay, weird. Doesn't pass to the next slide. Here it is. Weird, a lubricated interface is weaker in the sense that the lubricant reduces the friction coefficient, actually both the static and the dynamic. But it is tougher in the sense that it increases the fracture energy. And it took us quite a long time to realize that both has nothing to do. Weaker means that the helps the rupture to nucleate. It makes the interface more unstable, and then the rupture will start propagating for a lower stress. But tougher means that once the rupture propagates, more energy dissipated at the crack tip. But these are two different processes, nucleation and propagation. Why this result? We actually have possible reasons, but we were not able to check them because we don't have access to this frictional interface. We don't have access to this micrometric thick layer of contact. Our hypothesis is that maybe we have some layering transition of the liquid under pressure. This has been proposed by Granit, Klein, and Israelashvili, that under high pressure, a liquid can almost crystallize, but in an amorphous way, and then give some solid strength to the contact. The other hypothesis is that there is some elastic coupling between the liquid layer and the solid contact. In the group of Elisabeth Charlet, they have made some measurement under SFA of strengthening the contact by putting a liquid layer between the two solids. But for now, we don't have access to the frictional interface, and we don't know, but at least we have the evidence that the lubricant toughens the interface, and we will use it. Okay. Now, let's go to the title of this talk, the equation of motion of the crack. And the question here is if all the rupture speeds are accessible to the propagating rupture. Here you have an experiment where we have been able to trigger some slip event by adding a little bit of a torque to the block. And what you see here is the plot of the shear force versus time. And we have a sequence of slip events. And here we have the velocity profile of 3 ruptures coming from this slip sequence along the interface. And what you see here is that actually we have the red plot here is a rapid rupture that starts quite fast and accelerates up to the Rayleigh wave speed. And these rapid ruptures correspond to this event here, where the force was quite high when it has been triggered. But we also have this slow rupture here in blue that started very slowly, accelerated slowly as well, and then reached the end of the block. 150 millimeters is the frontier of the block. And this slow rupture corresponds to this tiny drop of force here. Then our question is, what determines the front velocity, the rupture speed that I will call CF of L, L being the rupture length. Then basically in fracture mechanics, this is what we call the rupture equation of motion. Then let's come back to fracture mechanics. Actually, the equation of motion is embedded into the propagation condition. The propagation condition of a crack is that G, the energy flux, is equal to gamma, the fracture energy dissipated at the crack tip. But this G here, the energy flux, will depend on the rupture length and on the rupture speed CF. Gamma, the fracture energy, is a material parameter. It can depend on CF, but this would be a structural response of the material to the rupture speed and not from dynamics. Then we won't consider a gamma of V here, of CF here. Then under certain conditions, actually this G can be splitted into 2 terms. A static one that we call the static energy release rate, GS, that depends on the rupture length and on the loading, times a dynamic correction, G of the rupture speed as a function of the rupture speed. And this is a non-dynamic correction. This is a universal function, doesn't depend on the system. And actually we can, if we can calculate GS, we do have access to the equation of motion, to the CF of L. Let's see how to calculate it. Then the energy release rate is then the dynamic correction G is for an infinite size system 1 minus CF over CR, CR being the Rayleigh wave speed. And the energy release rate GS goes like the static stress intensity factor squared divided by E, the Young modulus of the material. What is this KS? Sometimes it works, sometimes it doesn't. Okay, here it is. Then the static stress intensity factor, we know how to calculate it because we have access to handbooks where all the geometries are listed. Then we can choose our favorite. Then the stress intensity factor is equal to the integral over the crack path of the loading term, and I'll just come back to it right after, divided by the square root of L minus X, X being the axis of the crack propagation. The loading for a pure crack would be just the load I apply on the system. But here we don't have a pure crack, but a frictional crack where not all the stresses are released by propagation, but the crack only induces a drop of stress. Then actually our loading is the stress drop due to the propagation, then the initial shear stress minus the residual shear stress, what's left right after the rupture passed. And actually this quantity delta sigma, I have access to it experimentally because I do measure the elastic field during the rupture propagation, then I can measure the stress before, the stress after, and I do measure delta sigma. And that's what we do here for our 3 previous ruptures that I've shown you in this experiment series. We measure delta sigma, then stress before minus stress after, for all the strain gauges along the interface. Then we have about 20 strain gauges, and those are the dots that you see here. And on the other hand, we have access to the rupture dynamic with the contact area measurement. And actually this rate is imposed by the camera rate here. Now, just for simplicity, now knowing the drop of stress, I can calculate GS with the integral I've shown you just before. And then here I plot GS over gamma, gamma being the fracture energy of the material. Then this is GS for our 3 ruptures, and just note that GS equal gamma is the nucleation threshold. We cannot have a crack propagating under GS equal gamma. And then what I want to do, what I would like to have is CF of L, the evolution of the rupture speed with L, but just for the visual simplicity, we plot CF normalized by the Rayleigh wave speed, CR, as a function of GS over gamma. And the relation between these 2 quantities is just 1 over G. And you see here that our 3 rupture dynamics collapse on this master curves, which is just the prediction of fracture mechanics. Then this approach works very well. We understand that the dynamics of the rupture is just ruled by fracture mechanics. And if you are not convinced, I can put more ruptures on it, and it works pretty well. Then actually what we see here is that fracture mechanics not only describe the elastic field surrounding the rupture tip, but also the whole rupture dynamics. And also, this is slower and slower. Here it is. Yeah. And actually let me come back here. The difference between a slow rupture and a fast rupture is the excess of elastic energy that has been stored in the system. A slow rupture will propagate for a low initial loading, and there is just enough energy to make it propagating, but not for acceleration. While if the rupture nucleates for a high loading, then there is much more energy stored in the system than needed for propagation, and all the excess of energy goes into kinetic energy, and then the rupture accelerates. Then what we understand here is that fracture mechanics tells us that we can have slow rupture or fast ruptures with the same physical ingredients. The only difference is how much elastic energy has been stored in the system at the nucleation of the rupture. And this is a quite important point, that there is possibly no different physical mechanisms between slow and fast ruptures. And of course, there can be physical difference between slow and fast earthquakes. There are all this discussion about whether the fault properties can make a slow rupture to propagate or not. I'm not saying that the slow ruptures are only due to a low loading, but we say that we can understand it only by considering fracture mechanics. Okay, then this was for the propagation. What time is it? Ah, actually, I'm quite slow. Okay, this was for the rupture propagation, but now we can use the same equation of motion to predict the rupture arrest. We can make an experiment where the shear force looks more like that, where when we load the system, we have all this tiny drop of force until we enter into the classical stick-slip sequence. And actually what happens is that when we are in this stick-slip sequence, we observe spanning ruptures along the interface, but this tiny drop of force here correspond to arrested ruptures. What you see here is a rupture nucleating, here propagating, and just arresting at this point.
Sorry, Elsa,
Yes.
just a quick question. What is the difference in the loading conditions between these type of experiments and the ones you showed before where there
I'll
was
show
no
you.
arrested ruptures?
Yeah, I'll show you in the next slide.
Oh, okay, sorry.
The difference is that here we don't homogeneously shear apply the shear load. We push on the side. But actually, there are several configurations to observe arrested ruptures, and that's exactly what I wanted to discuss here. I'll try to do it quickly.
Okay.
Then what we will do here is to try to apply a crack arrest criterion to understand why the rupture arrests here. And this criterion has been proposed by Dave Kammer, and we provide the experimental validation with this experiment. Then if I come back to the equation of motion of a crack, we've seen this equation before, but now we are considering an arrest, and then at the arrest, this dynamic correction simply goes to 1 when CF goes to 0. Then now our arrest condition is GS equal gamma, and the GS is the same term that we have calculated just before, integrating the loading along the crack path. Then if we look at this arrest criterion, we understand that an arrest will occur when GS becomes smaller than gamma. And this can happen or because gamma becomes large, or because GS is reduced. And GS is reduced because delta sigma is reduced. And delta sigma has two terms. It's the initial stress minus the residual stress. Then a decay of GS can be due to a decay of the initial stress or an increase of the residual stress. And we'll start with the experiment you've seen on the previous slide, where we observe a decay of the normal stress. Then in order to get the plot you have just seen, we actually made this experiment where our two blocks are pressed together, and then we shear them using a pusher instead of using a stiff carrier under the block. And this is the main difference, because now what we have is that we have a concentration of shear stress at the corner near the pusher, while the initial stress decays along the interface. Then this is the configuration where we have a decay of the initial stress. Then doing that, we get this succession of arrested ruptures that you see here on the contact area measurement. The first arrested rupture is quite short, and then it gets longer and longer until the rupture 6, where it traverses the entire interface. And now what we want to do is to use our crack arrest criterion to predict the arrest location and compare it to the measured one. Then to do that, we need to calculate GS, and we need to know gamma, the fracture energy of the interface. Okay, then those are the initial stress for our 6 events. The yellow one is the event 1, and the blue one is the full event, the event 6. And you see that between events, the initial stress actually increases. And these here are the residual stress measured after each event. And as you see, the residual stress is constant. Then with these 2 measurements, we have access to the drop of stress here only for the event 2, the purple event. And from the drop of stress, we can calculate GS using our integral that we normalize by gamma. And then we say, okay, this is GS, and then the crack will arrest when GS becomes equal to gamma, to this location here. And we compare this location to the location measured on the contact area measurement. And we do that for all our events and for several experiments. And the results are on this plot where we have the y-axis is the predicted length using our crack arrest criterion, and the x-axis is the measured length of the event using our contact area measurement, and this line is 1. Then there is a perfect match between the prediction and the actual arrest of the rupture. And actually, this was the validation of the Dave crack arrest criterion. And I can just show you, it's 1 minute, that we can arrest a crack by increasing gamma. We have this tool of lubricant. When we apply a lubricant, we actually increase the fracture energy. Then if I apply a lubricant on only part of the interface, I actually create a step function in fracture energy along my interface. And now, by chance, in this experiment, the rupture nucleated in the dry part of the system and then started to propagate in the direction of the towards the lubricated part. What do we have? We can have events like that, where the rupture, then it nucleates here, propagates in the dry part, and then kept propagating in the lubricated part. Slower, but kept propagating. But we can also have this kind of event where the rupture just arrested at the corner of the lubricated part. And we can even be quantitative about it. Same calculation, nothing new. We calculate GS by measuring our stress drop during the propagation. We know gamma. And for the event A that was propagating, the GS profile is like that. This is GS in the dry part, larger than gamma dry, and it propagates. And when it enters into the lubricated part, it actually was equal to the fracture energy of the lubricated part and kept propagating. While for this event B, what happened is that at the corner of the lubricated part, GS was smaller than the fracture energy, and then it stopped. And actually, it's nice because we use a lubricant to arrest a rupture and therefore to delay the onset of sliding of this system. Because then this arrested rupture didn't allow the whole system to slide. And this is totally okay in terms of fracture mechanics. Okay. let's jump to the conclusion. Yes, some comments about the relevance for earthquake science. The question is, what can arrest an earthquake based on fracture mechanics? Then based on fracture mechanics, the arrest criterion is GS equal gamma. GS has an integrated effect due to the fact that we integrate the loading over the crack path, while gamma has a local effect and can suddenly arrest a crack. And it seemed to us that it was quite of a controversy. Sorry, I tried to go to the next slide. It's just text. I don't know why it doesn't move. Ah, here it is. It seems that it's quite a controversy that some people claim that an arrest is due to a lack of loading, while other people claim that an arrest is due to a barrier along the rupture path. And we say, okay, both are okay in terms of fracture mechanics. And just to mention that this same criterion has been tested by Kay, Kammer, and McClaskey on a 3-meter long granite fault, and it actually works very well on this system as well. Okay, here it is. Then we've seen that at the onset of sliding, there is a rupture propagating along the fault, and that this rupture is a shear crack. Shear crack by the fact that the strain fields are described by fracture mechanics, and by the fact that its dynamics is described by fracture mechanics, both propagation and arrest. I want to stress that the fracture paradigm is very different from the friction coefficient paradigm to understand friction, because friction coefficient is based on force balance, while fracture mechanics is based on local energy balance. And some warning about applying fracture mechanics. It applies so nicely if we consider a homogeneous system, same materials on both sides. Bimaterial system have a different way of breaking. The comment we had at the beginning that we need a separation of scales between the process zone and the elastic zone. And we need the energy balance to be satisfied at the rupture tip. And of course, damages, thermal pressurization can prevent this energy balance to be very local. Thank you.
Wonderful talk, Elsa. Please, I'll invite everyone, unmute yourself and join me in thanking Elsa for a fabulous talk.